So today we're going to talk about spring mass oscillations for Physics Lab 7. The objectives were to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. We're going to use Newton's second law and the energy principle to predict the motion. And then we're going to test to see if the sum of the energies in the system add to zero. Last objective is to predict the motion of the system using Newton's fundamental principle. F equals mass times acceleration, and the energy principle, delta E, change in energy, equals work. So we have here an oscillation graph from tracker, and the mass was released from rest, which equates to initial velocity being equal to 0. We take the initial position from tracker for the mass, and we also use the tracker to get the period of oscillation. And in order to get the period of oscillation, we do the time. For example, we have the time here, so we can look here and see, okay, at about, at about 2, or should I say 3.2-ish, around there, there are about 2 oscillations. So we can do the number of oscillations divided by the time, and roughly 3.26 divided by 2 oscillations, and that'll get you the period. So next, looking at initial calculations, we have outlined here, time divided by number of oscillations gives you the period. We have spring stiffness, formula for that, 4 pi squared times mass over time squared. And when we do calculations, we get Ks is about 6.05. And then we have the relaxed length calculation here, LO equals magnitude of L minus mg over Ks. As for Newton's second law, we have here final velocity equals the initial velocity plus total F net divided by mass times delta T. For the position, we have our final position equals initial position plus the velocity times change in time. F net is going to, the total pushes and pulls are going to be the sum of F gravity plus F spring. In this case, F gravity being negative because the force of gravity is pulling down on the spring. And then we have the formula here for F spring. So Newton's second law, the code using Python for that I have outlined here, as you can see. We have F gravity and F spring, which I just talked about. They sum up to give you F net. And we use the net force, which is composed of the two, F gravity and F spring, as I just said, in order to find the velocity of the ball. And then we use the velocity of the ball to calculate the new position of the ball, which we have outlined in these pieces of code here. Next, we'll look at the energy principle. We know that the surroundings are not acting on the system. So therefore, there is no interaction from the surroundings, which therefore means that work equals 0. Therefore, delta E equals 0. And then we also have here, we know that delta E equals work, which equals change in K plus change in potential gravitational plus change in potential energy. And then we have U spring and U grav, the formulas for those outlined here. Now let's focus on the code used for the energy principle. So these lines here represent the updated kinetic energy, which are compared to the initial energies calculated outside of the loop. But this is the code represented inside the loop. We use these lines of code to find K, delta UG, delta US, which are then summed up to find the total change in energy. So we go down to what does it mean? For your model, is the energy principle satisfied? Well, we're looking at the screenshots here. The first image we have here represents a spring mass system where the blue ball represents the predicted motion and then the red ball represents the observed motion. You can see from this image that the red and the blue ball don't line up exactly, which can be a result of the difference in the intervals used in VPython compared to Tracker. We'll go up here to the actual graph of the energies. The yellow line represents total energy. Green represents potential gravitational energy. Red represents change in the change in the spring. Blue, change in kinetic. And as you can see from the image, E total is 0, the yellow line. U grav increases as U spring decreases, and U spring increases as U grav decreases. And with all that said, the energy principle is satisfied. Now looking at the second question, using the data you obtain in Tracker, making two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillations from the y position data. Compare the two estimates and discuss. So when looking at the graphs here for the x and y, we can calculate the periods as shown before. And in doing that, we get, when I do calculation, I get a period of oscillation for the y component to be about 1.58, and then the x component to be about 1.63. Therefore, the system is spending more time oscillating in the x direction than it is oscillating in the y direction. Thank you.